This video is going to focus how to solve logarithmic and exponential equations. So by the end, you should know how to solve logarithmic functions as well as exponential functions. So the first scenario that we're going to look at is when an equation involves only logarithmic terms. So if an equation involves only logarithmic terms, then we can set what's sitting in the spots of u and v equal to each other. Now the bases of each of those logs, notice, have to be the same. The catch with this, though, is that you can only have a single log on each side of the equal sign. So look at what we've been given in this equation here. Log x equals log of x plus 3 minus the log of x minus 1. So the first thing you're going to have to do is use that quotient property to write this right-hand side as one log. So we still have log of x on the left-hand side. But on the right-hand side, we're going to have log and then x plus 3 in the numerator and an x minus 1 in the denominator. Now that we just have a single log on each side, we can set what is sitting in the spot that I'm putting a blue box around equal to each other. So that's what I've done up here. We've got x equals x plus 3 over x minus 1. So we have to use some algebra here. So I'm going to put a 1 underneath of that x, and we're going to use cross products. We're going to multiply on the red diagonal. That's what gives x times the quantity x minus 1. And then I'm going to multiply on the blue diagonal, and that's what just gives us x plus 3. It's been multiplied by 1, but we don't see it there. So we have to distribute our x, so we get x squared minus x equals x plus 3. And when we clean it up, it turns into a quadratic, which we can then factor to x minus 3 and x plus 1. So we end up with two solutions, either x equals 3 or x equals negative 1. What we have to remember, though, is that this was actually a log to begin with. So we're not going to allow any answers that allow the logs to be negative. We call that an extraneous root. It's extra. So the only solution that we have is x equals 3. Let's look at another one. Let's suppose we've got log base 3 of 6x minus 2 is equal to 2. A lot of people prefer ones that look like what I'm underlining in red because I don't need to worry about having a log on both sides. The best way to solve that is to rewrite it as an exponential. So we've got 3 squared equals 6x minus 2, or 9 is equal to 6x minus 2. If we add 2 to both sides, we get 11 is equal to 6x, which we can then divide by 6. So x is equal to 11 over 6. For the second example, we don't have a log on both sides, but we do still need to get a single log on the left-hand side. So we're going to rewrite this as log, and then x minus 1, x plus 2, and that's going to still be equal to 1. Now I can use the same strategy that we used up here and rewrite it as an exponential, but it doesn't look like we have a base. So you have to remember the properties, and the property says if there's no base there, we can assume that it's a 10. So I'm going to rewrite this as 10 to the first power is equal to x minus 1 times x plus 2. Let's go ahead and get a fresh sheet to solve that. So what we have is 10 is equal to, and we're going to FOIL. So first gives us x squared, outer gives us 2x, inner gives us negative x, last gives us negative 2. So 10 is equal to x squared plus x minus 2, and we need to subtract the 10 from both sides so that it's set equal to 0. 0 is equal to x squared plus x minus 12. And we're going to go ahead and factor that. So we need two numbers that multiply to negative 12, but when we add them, we get positive 1. So that's going to be a 4 and a negative 3. So our two solutions are x equals negative 4 and x equals positive 3. Let's check to see if any of those are extra. So in looking back to the initial problem, which involved log of x minus 1 and log of x plus 2, this negative 4 is not going to work. But 3, when we plug it in, keeps those numbers positive, so our solution is x equals 3. So let's switch gears and look at some exponential equations. So if we have two exponentials, just like with the logarithms, we set the u and v equal. If the bases are the same, all you have to set equal to solve for are the exponents. And keep in mind, if there's an exponent, if you take a log or natural log of each side, that will pull that exponent down in front. Let's see how this works. First of all, to solve exponentials, each side must be written having the same base. So if we are given 9 to the x equals 27, first we need to write both sides as powers of the same base. So we can rewrite 9 to be 3 squared and 27 to be 3 cubed. And that's what's happening in this second step right here. So now they've got the same base. They each have a base of 3. So we've got 3 to the 2x is equal to 3 cubed. Since the 3's match, we can almost pretend like they're not there. And we're going to set the exponents equal. We're going to go ahead and divide both sides by 2. So in this case, x is equal to 3/2. Sometimes it's just not possible to make each side have the same base. Look at 3 to the x equals 5. 3 and 5 are both prime, so I know that I can't get their bases to match. But what I can do is take a natural log of both sides. What that will do is allow this x to slide out into the front. So we're going to end up with x times the natural log of 3 is equal to the natural log of 5. We can go ahead and solve for x by dividing both sides by the natural log of 3. And this is going to be a calculator problem. You're going to end up with a decimal answer for this. Finally, let's look at an application problem. According to data from the U.S. Federal Reserve, the amount of outstanding consumer debt in trillions is approximated by the function you see underlined in red, where t equals 0 corresponds to the year 1980. Suppose that we want to know in which year the consumer debt is going to be 4 trillion. Let's go ahead and work that problem out. So I'm going to go ahead and start with the 4. Let's plug that in. The first thing that we need to do to solve this equation is to divide by the 0.365478. So I'm going to do that to each side. So these guys are gone. And so now on the right, we've got 1.073306 to the t. And on the right-hand side, I'm just going to rewrite this still as a fraction. Okay. Now I need to get t, but the only way to get t is to take a natural log of both sides. So I'm going to take a natural log of the right and a natural log of the left. What that's going to do is it's going to allow this t to fall down to the front. So I've got t times the natural log of that 1.073306, and I've got the natural log of this whole fraction here. And so to solve for t, now we can divide by the natural log of the 1.073306. So it's nasty looking. Definitely a calculator problem. Okay, so what you're going to do in your calculator is hit the natural log button, parentheses 4 divided by 0.365478. Close the parentheses and hit enter. And then divide that answer by what you see in red there, the natural log of 1.073306. When you do that on your calculator, you're going to get an answer of approximately 33.82. So remember that t equals 0 corresponded to the year 1980. So this is happening sometime during the 33rd year. Don't be so used to rounding that you round that to 34. We know that it's happening in the 33rd year. We don't need to round. It's going to happen in the year 2013. I don't want to say it's going to happen in 2014 because it doesn't. It's somewhere in the 2013 year that this happens. I'd like for you to try this now with the number 5. Put a 5 in. Everywhere where you saw us, put a 4 in. And let's see if you can get the correct year. I want you to enter the year you get to the screen at the right. And once you've done that, you can go ahead and start your assignments.